Hello, everyone, and welcome to the lecture 7 of the deep learning course for NLP. Today, I'm going to talk about recurrent neural networks, which was and still is an effective neural architecture for natural language processing. Specifically, we discuss recurrent neural networks, and then we'll take a look at vanishing and explosion problems in these neural models, and then we discuss two types of recurrent neural networks named GRU and LSTMs. And at the end, we take a look at some applications of RNNs in natural language processing. So let's start. If you remember, we started the course with multi-layer perceptron architecture, or MLP. Multi-layer perceptron neural network consists of one input layer, which is at the bottom, that takes an input and maps that to some feature vectors or some embeddings. And then we have several hidden layers. So like it can be one or more than one hidden layers. In this example, we have two hidden layers. And at the top or at the end, we have one output layer. Output layer usually shows the estimates the probability of the probability of the labels given the input X. As usual, we use the notation X to refer to the input vector. So let's say X would be a vector named x1, x2, x3, x4. So a vector with 4 or 5 elements. It doesn't matter how many items that we have. So we use the notation of norm of X to refer to the length of the input vector. So the first layer, or the input layer, has the length of the number or the dimension of the input representation, right? Or the input vector. And then we multiply this input vector X by a matrix named W, and we add a bias term to it. So this is like a linear operation, right? So you multiply the input X by a matrix W, and you add a bias term to the output of this multiplication. So you obtain XW1 and XW2. And then we usually use some activation function like F to have some nonlinear, to add some nonlinearity to our neural model, right? So the output of this activation function is the vector representation of the input at hidden layer 1, right? This activation function can be tangent hyperbolic, can be sigmoid function, can be rectified linear unit. So we in the previous lecture, we discussed different types of activation functions and the advantages and disadvantages of these functions. But so to keep it quite general, we use the notation F to refer to the activation function, right? And then we take the output, or we take the vector representation of the input in the first layer, which is H1, And we do this linear operation again, this time on H1. So we try to transform H1 with some nonlinear function, so which is f, and the output would be the vector representation of input again at the second hidden layer. So we have H2 here. So the dimensionality of H2 doesn't need to be necessarily similar to the dimensionality of H1. So H2, for example, here has 4 nodes, or just like 4 elements in the vector, but in H1 we have only 3 elements. And at the end, we do the similar operation here to get the vector representation over the labels or over the outputs that we have. And we use y hat notation to refer to the prediction of the model. So if the gold label or if the true labels in the training set will be shown by only y, we use y hat to say that, okay, so this is a prediction of y. So this is not a true y, this is a predicted y. And y consists of 2 elements because we have 2 nodes here, right? So this is the usual way that we process an input x and we give it to the MLP, to an MLP, and we process that in several layers with some nonlinearity, and at the end we get the output vectors. Okay, to keep it a bit simple, so what we do is that we use this notation to refer to MLP in general, and a specific type of MLP, which is feed-forward layer or feed-forward neural models. The main idea is that if we have a vector x as the input, we multiply that by a matrix like U, right? And then we get, with some nonlinearity at the hidden layer, we get the output vector H1 at hidden layer 1, and then we multiply this H1, this H by a weight matrix named V to get the output prediction of the model, of the network or our model. The main property of the feed-forward neural models is that we only have one hidden layer. So we do not have more than one hidden layer. But in MLP in general, we can have more than one layer. So we can have really deep neural models. So you can say feed-forward is an MLP with only one hidden layer, or we can say that MLP is a deep connection of different feed-forward neural layers. Okay, but what is important here in this slide is to know that we use this notation U as a matrix to transform an input vector X to a hidden layer H, and then we use matrix V to transform the hidden layer vector, the vector representation at the hidden layer, to the output vector. The other thing that is important is that we have only one vector as the input. So the input is like one vector, and we want to do the prediction on this, right? Okay, now we can discuss about our motivation for having recurrent neural networks or RNNs. But when we look at text is usually a sequence of symbols, right? So for example, a word is a sequence of characters. So we have a structure over symbols in a text. If we look at a sentence is usually a sequence of words. So as a human being, when we read a text, we usually, like in several languages, we read from left to right, but in some other languages, we read from the right to left. But what is important is that we process text sentence by or sequence by symbol by symbol, word by word, character by character, sentence by sentence, paragraph by paragraph, and so on. So we process a text as a sequence. And the point is that usually there are certain dependencies over different elements in this sequence. And we as a human, we can understand the text by just processing that sequentially. So elements or symbols in a text are not independent from each other, but they are dependent, and they can have short and long dependencies. Like the first word in the text can be related to the word 100 in the text, or they can be, but usually the dependencies are defined over like a short context. So let's say if the input text would be like a Persian cat sat on the mat, the input is usually like a sequence of words. So we have x1 equals to A, x2 is like Persian, x3 is cat, x4 sat, and x5 on, and so on. So this is the input. So we have a sequence of words. So we do not have one independent input like X. We have the input is a sequence of items or a sequence of symbols, and each of these symbols can be presented by a vector. So the input is a sequence of vectors, and it's not only one vector. It's usually a sequence of vector. Okay. As such symbols are related to each other in text, so should symbols representations, right? So if we know that like Persian cat, Persian is the adjective for the cat. So when we read it, a Persian cat, so as a reader, we understand that, okay, so we are not talking about any sort of cat, and we are specifically talking about Persian type of cats. So the representation of a Persian cat should be different with the presentation of a cat in general, right? So the question is, how can we relate representation of symbols to each other? So we know that in the text, symbols are related. So in the embedding space, the vector should be next close to each other or somehow represent this relatedness in the language. How can we do it? So this is the main motivation for the recurrent neural models. So if x1 would be the first symbol, or let's say for simplicity, we say x1 represent the first word, or it would be the word embedding of the first word. We give it to a feed-forward neural model. So we have H1, and then we get the output for this token, or the embedding representation of this token, or a vector representation for this token. And then we use the hidden state as a memory to memorize, okay, what we have observed so far in the sequence. So we only observe the first word, and we multiply that by another matrix like W to transform the information from the memory for processing the next token. So when we see the second token like X2, this is like the embedding representation of the second token, like Persian. We multiply that by U matrix because we want to move it to like to the memory. But the memory will not be updated only based on the input token. But the memory will be updated based on both input token and what we have observed so far. So the memory like H2 or the hidden state H2 represents the content that we have observed or we have seen like A or like X1. And it says, okay, so the memory so far was like H1, and now that the input is X2, the new memory would be H2. And based on H2, we provide a vector representation for the output. So H2 somehow presents, if X1 is A and X2 is Persian, then H2 represents a Persian, like the phrase a Persian, right? And the prediction that we have as Y2 or Y for the second token, Y hat 2, this prediction is conditioned on the phrase a Persian. So it's not conditioned only on Persian, but the whole phrase. Okay, and if we continue and we see cat, a Persian cat, then we do this procedure again. So we see cat and we multiply that by u. So we update the hidden state again with respect to the token that we are seeing in this step, like X3, and H3 represents the whole phrase a Persian cat, and the vector representation of the output would be conditioned on the whole phrase Persian cat. So it's it's conditioned on from the first token to the last token. It doesn't matter how long the sequence is. The main idea is that if we have this memory cell like the hidden state, we can store information for representing the future tokens that we will see. Okay. What is important to notice here is that the parameters U, V, and W are shared among different recurrences or even over different iterations. Meaning that for processing a token to a hidden state, to the hidden state, we always use matrix U, right? It doesn't matter in which step we always use matrix U to map input vector X to the hidden state, right? So this vector is fixed, or this matrix is fixed, and we use it, right? We always use V to transform a hidden state to an output vector like Y hat, right? So it doesn't matter again in which step we always use matrix V, and we always use matrix W to transform a hidden state from a previous step to the hidden state of the current state. And these U, V, and W are trainable parameters. So when we process the whole sequence, these U, V, and W are fixed, and we compute the vector representation at each time step. And when we get to the end of the sequence and we want to update the parameters, we update the whole parameters, and then we compute or we do the forward pass on the whole sequence one more time. All right. Okay, if we want to use a simple notation to say how to show or to illustrate how recurrent neural models work. So the main idea is like this. So we, at each time step or at any time step, like T, we take the token representation, like the embedding representation of the word or the symbol, like XT. We use matrix U to map that to the hidden state, and then we use the hidden state and transform that to the output state or to the output vector by matrix V. And at the end, what is important to know that the hidden state at each time step is calculated or is computed based on two input vectors, the value of the hidden state from the previous step and the current token or the current token representation at the current step. Okay. So if we want to do it in math, so we, as the input, we usually have a sequence of vectors, right? So let's say if we have tokens x1, x2, x3, we use the boldface notation to show their vector representations or their embeddings. So the input as a text is usually a sequence of vectors like x1 to xn. And it is important to note here that each of these items is a vector. So it's not one number. So that's why we have xt here. So let me use my pen. Okay, it's here. Okay, what is important is to notice here that xt is a vector with size of x. So you can see if x is a word, then its vector representation can be obtained by a pre-trained word embedding. So if for example, if x1 is x2 is Persian and x3 is cat, then bold x1 represents the word embedding of a, and x2 represents the bold embedding of the word embedding of Persian, and x3 represents the word embedding of cat, right? So they can have dimensionality of norm of x, so which is like 300 or something like this. Okay, and then what we need to calculate is the value of the vector representation of the hidden state or memory. So the hidden state, ht, at time step, as at each time step, is that a matrix multiplication of u and the current vector representation. And we take the value of the hidden state from the previous hidden state, and multiply that by w. And we use a bias term that is allocated to the hidden state, right? So it's a very simple approach to calculate the hidden state, right? So just you use the linearity that we always use in multi-layer perceptron. So you multiply each input by a matrix and sum them up. So this is like the approach in neural model always. So you multiply the inputs by some matrix, and then you sum them up and give them to some activation function, or give the output to some activation function. So let me move to here. So the activation function is here, for example, f. So this activation function is used for hidden state. So it doesn't need to be identical with the activation function that we use for the output state, but if it's for the output vector, but it can be identical, but it doesn't need to be. Okay, so U is a matrix with size of X times H, and H is the dimensionality of hidden states, and it is like a hyperparameter. So when you are defining your recurrent neural network, you need to define, okay, what should be the length of the vectors or the number of neurons in the hidden state. So if you give, for example, if the word embedding is 300, do you want to have a 400 representation in the hidden state, or a representation with length of 100? So this is like a hyperparameter, and you give it as the input to the model. But based on that, everything would be calculated. So this is the only hyperparameter that we have. So if we say H is the dimensionality of the hidden state, then U, the size of the matrix, is clear, right? So the size of the matrix is the size of your embeddings times the size of the hidden state, or the dimensionality of the hidden states. And W is another matrix, but W takes the hidden state, the value of the hidden states in the previous step. So it's the size of the hidden state in the previous step is still H. So the norm of H, and you multiply that by norm of H, because you want to keep the size as it is. And then bias is a vector with size of the hidden state, because at each neuron you add one bias term. All right. Okay, now we have the hidden state computed based on two inputs. Based on both inputs, the current token, which is xt, the current token representation, which is xt, and the vector representation, or the value of the hidden state in the previous step, which is ht minus 1. So this hidden state representation now can be used to predict an output for this token, or like a vector representation for this token, or for the sequence until this step. So the only thing that we need to do, as always, is that we take ht and we multiply that by a matrix like V, and add a bias term that is associated only to the output layer, and the size of the V is equal to the size of actually V is a matrix with the size of H times norm of H times norm of Y hat, and then the size of the bias is a vector with size of norm of Y hat, or like the number of output labels that we have. Okay, so so that's it. So this is a very easy way to implement recurrent neural networks, and the only thing that we should note here is that, or we should emphasize here, is that matrices W, U, and V are shared parameters between different time steps. So you do not reinitialize them, or you do not change them, or you do not do backpropagation. So you keep them fixed until you process the whole sequence in the simplest way. You process the whole sequence, and at the end, you have a vector representation of whole sequence. The second point here is that at each time step, ST, or the vector representation at the hidden state, can be taken as the vector representation of the whole phrase that you have observed so far. For example, in our example, so it's better to move to the next slide. So let me clean my drawings. Oh yeah. Okay, so then here, here it's better. We can discuss about how we can train the model. So let's say as the input we have a sequence of vectors x1 to xn, and as the output we want to get a sequence of outputs like y1 to yn. And as always, we can define a loss function, right? The loss of a sequence prediction is the mean of step losses. So the point is that at each step, we have a prediction. So we are doing a prediction at each time step. And we can make a mistake at each of these time steps. But how should we know how much error do we have for the whole sequence? The easiest, or the most straightforward approach, is to take the mean of the errors at each time steps, right? So if we say LT is the loss at time step T for true label YT and the predicted label Y hat T, we just compute the average for a sequence of n. And simply, now that you have the loss at the end of the sequence, you can compute the backpropagation. You can run the backpropagation algorithm to compute the gradients and use stochastic gradients to update parameters, which are W, V, and U. And when you update all parameters, you fix them, you process the sequence again, and then you calculate the loss and go for over. So, and the idea is that if you update the parameters to work well for all time steps, then the model should obtain the good representation of input sequences. Yeah, as I said, hidden states. The hidden state in RNN is known also as memory. So because it captures the representation of the input sequence from left to right, from the first token until the current token. And if you remember, in some types of word embeddings like glove and word to wake, these word embeddings are independent. So for X1, no matter in which context it appears, you provide a vector representation, right? And for X2, you provide a vector representation independent of its context. With the help of RNN, you can condition these representations on each other, right? So you can say, okay, if X1 appears before X2, or X1 is before X2, then X2 representation, or the hidden state representation of X2 represents both X1 and X2. It's conditioned on X1 and X2. In principle, the hidden state represents information from the first step until the current step, conditioned on current input symbol, right? So RNNs can capture left to right order of input symbols. Okay, so let's do it manually, and we check how RNN works on our example. So as the input, we have like a sequence of tokens, like a Persian cat, like a phrase, right? And we usually know that each if we use glove or word to wake, for example, we get a vector representation for each word independent of its context. So if we have a for determiner for the article A, we get the value, a vector representation. For Persian, we get a vector representation no matter if it is a cat or if it is, or before that is a. And as the output, let's say we want to predict the part of a speech tag of the token. So for the first token, we should say that A is the determiner, Persian is the adjective, and cat is the noun. Okay, and let's say our embedding function returns this vector for A, and it returns this vector for Persian and this vector for cat. And for the output vectors, we also used one hot vector representation. And let's say with dimensionality of 4, and this is y1, this is y2, and this is y3. Since the task is a sequence prediction, we can focus on RNN. So whenever we have sequence prediction, it's always go for RNN. And so if it is RNN as a hyperparameter, we should define the size or the dimensionality of the hidden state, which is, let's say we say 2, and we have some activation function or nonlinearity, actually 2 activation functions. The first activation function F is used for the hidden state, and we define it as a rectified linear unit. And the second activation function is used for the output layer, or y hat, which we use softmax. Why? Because we want to predict some probability scores for different over different POS tags. Let's say we initialize our RNN's parameters by random values like U, W, and V, like this. And for simplicity, we set the bias terms to 0 vectors. And since like RNN is a recurrence model, we need some initial value for the hidden state, like because for the first token, we do not have any token representation or any value in the hidden state. So we need to initialize it as well. So we simply initialize it with 0. So 0 is the input. And now we can calculate the output of this matrix in this RNN. So let me use my pen and we can go through this together. Okay. Okay, so first we visit X1. So let me change the color. Okay, first we visit X1. And we take the vector representation of X1, which is 1, 0, 0. We multiply that by matrix U, and we get the hidden state value H1. The first thing that we should notice is that the value of U is fixed over different time steps. So the parameters are shared over time steps. So we do not update the parameters. We do not change the parameters until we finish, like in the simplest scenario, until we finish the whole sequence. As I said, so this is the simplest or the basic way to process RNNs. And then the hidden state here at the first step only has only one input because we assume that the hidden state is initialized by zero, and then we multiply that by the V matrix, so 1, 1, to get the vector representation for the output. Right, so this is like the probability of labels, and then we use the gold label to compute the loss, which is if we use the log likelihood, for example, then this is the log of 0.37, right? Okay. Now that we have X2, here is more important. So at the second step, we take the vector representation of X2. So this is, if you look at here, we multiply that by U, so by this matrix, and then we sum that with a weight, a weighted representation of the previous hidden state. So this is like HT minus 1 times W. So the second input comes from the previous state. So we multiply the previous state by a matrix W to transform this matrix to transform this hidden state to a vector representation for the second hidden state. And we add a bias term, which we assume is 0, and we obtain the vector representation for the hidden state, given some rectified linear unit activation function. It is important to note that if the input here is A and here is Persian, this vector 5 and 4, this vector shows the representation of a Persian, right? A Persian, but it doesn't show the representation of a Persian cat. It does represent a Persian only, okay? And now in the third step, we take the vector representation of cat We multiply that with the matrix that we have in matrix U, and as the second input, we multiply the hidden state representation at step 2 with matrix W, and we use a rectified linear unit activation function, and we take this vector as the value of the hidden state at the third step. It is important to note that the value of the hidden state at third step represents the whole phrase, like a Persian cat. So if you want to have a vector for a Persian cat, you can use the last token representation, right? Okay. And then, for example, for the third step, you multiply this hidden state by vector v, and you run it by a softmax function. You compare with the gold label, and you compute the loss function. So the loss, as I said, is the average over the loss per steps. And after having the loss over the whole sequence, you're ready to compute or update your parameters. So for updating the parameters, we compute the gradients using backpropagation. So just like we have the loss, we give it to some PyTorch or some deep learning framework, and that deep learning framework usually computes the gradients for us. The only thing that you should keep in mind is that parameters of RNNs are shared through time steps. So, so what does that? Why is it important, and why am I emphasizing on this so much? The main reason is that this shared parameter and deep relations between tokens may cause some issues in the follow that we will discuss in the next steps, in the next slides. Is sometimes in some literature, backpropagation for RNNs is called backprop through time. So it's BPTT. So if you see this term, don't get confused. It's like backpropagation through time because you process a sequence of inputs, and then you, at the end of the sequence or at some point at the sequence, you decide to backpropagate, right? So you stop processing, you backpropagate and update your parameters. We don't need to go through the details of calculating the gradients here, as deep learning frameworks compute the gradients for us. But if you would like to compute gradients brute force, you can do that manually. So just like for each weight, like W, you compute the gradient just by computing like the difference between the values of the loss for one weight and like a slight change in the weight, and then you update the weights after gradient computation as the way that you do in stochastic gradient descent. Okay. This story of learning the whole sequence can be problematic when you have a very, very long sequence. We have seen in the previous like in previous lectures that if we have multi-layer perceptrons and we increase the number of hidden states, the gradient at the lower at the early layers can become zero easily, or just they can vanish or disappear, meaning that by changing the vectors at the early layers, you will not see any change in the output layers. Okay, so most of the updates is happening in the top layers. RNN, although it looks like one layer, but since we have recurrent step in it, it can be seen as a very, very deep neural model with sparse and skip connections. With sparse connections because you shared parameters, and skip connections because the vector representation at the output vector at step 3 depends on hidden state 1, 2, 3, right? So just like you have skip connections here. Vector representation at step 10, you have vector it depends on vector representation or the hidden state of step 1, 2 until 9, right? Or until 10. So as I said, the output of the last steps are calculated based on the hidden state vectors at early steps. So if you want, as we can have two recalls here, we said that the value of the hidden state ht is at time step t is the output of an activation function on the linear combination of the input vector and the value of the hidden state in the previous step. So if just for easiness, so for easiness, if we use notation ZTH to say to represent the linear combination of xt and ht minus 1, like the input representation and the representation of the input token and the value of the hidden state in the previous step. And if we combine these two linearly and we present this combination by ZT, then HT is like a nonlinear form of ZT, right? So it's like rectified linear unit, or it's like sigmoid or tangent hyperbolic of ZT. Okay. And the other thing is that the way that we calculate the output, so it's like y hat. Y hat is also the output of an activation function over the linear representation of the hidden state. So if we compute the linear representation of the hidden state, then y hat is a nonlinear form of this linear transformation, right? Okay, so the only difference here is with the previous slide is that I split the equations into two parts actually. In the first part, I calculate the linear form or the linear combination of the input vectors. And in the second part, I calculate the nonlinearity of the linear combinations. Okay. Let's see what happens if we have only two steps. If we have only two steps, we need to calculate the loss. So let me again use my pen. We need to calculate the loss for two steps. So like in a simple scenario that we have a sequence with two inputs, right? We want to calculate, and we only calculate here. The only thing that we show here is the gradient of loss with respect to matrix W which transforms a hidden state layer by layer, which this matrix actually creates the deep structure in RNN, right? Because it is the main matrix in recurrence that happens in the recurrence steps. As we discussed, the loss of the whole sequence can be the average, or just like for simplicity, we take the sum. So it's the loss over the first layer plus the loss in the second layer. So the only thing that we need to calculate is the loss, the norm, or like the derivative of L1 with respect to W and the derivative of L2 with respect to W. Okay, so let's start with the derivative of L1 with respect to W. The L1 is the difference between Y hat and Y, right? So we need to calculate the derivative of L1 with respect to the predicted output, Y hat. And then here we see the chain, Y hat depends on ZT. So you can always say, you take the derivative from the inside of the parenthesis first, and then you take the derivative of the function itself. So then you have the derivative of Y hat with respect to ZT. But since it is in the step 1, so T equals to 1. And then you have, so here we have the derivative of Y hat with respect to the inside of the parentheses, and then we have the derivative of Z1 with respect to HT, right? So the derivative of Y hat with respect to the function, and then you have the derivative of ZT with respect to H1. And then, okay, H1 relates also on ZH1. So you calculate the derivative of H1 with respect to derivative of, with respect to Z1 H, and then Z itself depends, ZH itself depends on W. So just like we now calculate the derivative of Z1H with respect to W, right? So if we only look at this part, derivative of H1 with respect to Z, which is here, the derivative of this function, we can say that, and F is the activation function of the hidden state, right? So it's only the derivative of the activation function, nothing more. So, and we can say the derivative of L1 with respect to W is a factor of the derivative of the activation function for the hidden state. Is that correct? So let's say we forget everything about the other derivative, and we just say any number that we get is still a factor of the gradient of H1 with respect to Z1. Okay. For the first step, it's easy, but now we go for the second step. For the second step, we need to calculate the loss L2. So let me clear all the hidings. So what we do, we need to calculate the gradient of L2 with respect to W. So we start from the output L2 with respect to Y hat 2, Y hat 2 with respect to Z2 Y hat, and then we calculate the the gradient of Z2 Y hat with respect to H2, and the gradient of H2 with respect to Z2, right? So the gradient of H2 with respect to Z2 is like here, right? H2 with respect to Z2. Here is the case. So Z2 we need to calculate the gradient of Z2 with respect to W, right? But we should be HT1, but we should be HT1, but HT1 is it's not a fixed value. It's also a function of the former steps. It's like a function of the value of the hidden states in previous states. So H1 is the output of this function, which is obtained based on Z1, right? So the derivative of H2 with respect to the derivative of Z2 with respect to W that we want to calculate is equals to H1, so the value that we have, times the norm of H1 with respect to Z1, times the norm of Z1 with respect to W. And the main point here is that the hidden state, or in the value of the hidden state in the previous step, is a function, actually, is the output of a function in which is obtained based on earlier steps, right? So that's why we have a deep structure. So we don't rely on the value that we have, but we need to also compute the gradient backwards. So we need to go to the earlier steps. So again, if we only look at the gradient of this activation function here, which is this part and this part, right? These two. If we look at these two and we say that the gradient of L2 with respect to W is a factor of the gradient of this activation function, but the point is that since it happens in the second step, is a factor with magnitude 2 actually for of this activation function So it gets worse. So if here we only rely on one derivative, here we rely on two derivatives of this activation function. And since we multiply them, this can yield problem in computer science, right? For 2 steps, it's clear. Now, what if we have 3 steps? If you have 3 steps, then you calculate the loss for 3 steps for each of these steps. And if you notice, the loss in the first step relies on or is a factor of the derivative of that activation function, the activation function for the hidden state in one time or the only tougher time at step 1. And then the activation and then the derivative of the second loss with respect to W is a factor of the derivative of the activation function of the hidden state in the first and the second state, and at the third step we have the derivative of the activation function 3 times, like from the first step until the third step. So you can expect that if we have n steps, then the derivative of the loss is at the last step, like step n, contains n, is a factor of multiplication of the product of n derivatives of the activation function that you define for the hidden state. Okay, but why is it a problem? The problem is that if we have this product, if we say that the gradient at the last step depends on the multiplication of many numbers, of many gradients. If all gradients in the chain are greater than 1, like number 1, if greater than value 1, then their multiplications explodes, right? So if all the values are greater than 1, so you are multiplying many numbers that, or like at least n numbers that are greater than 1. So if you have very large number L, very large, if you have very long sequence, then it's very likely that the output of this multiplication overflows, and as the result, the norm of the loss or the gradient of the loss with respect to W which results in NaN value. But on the other hand, if one of these gradients is close to 0, or if all gradients are less than 1, then their multiplication vanishes easily. And so because you multiply many 0 values or many values that are close to 0, or if one of them is 0, just like in one step the gradient is 0, then it's very likely that the whole sequence, I mean, it's not likely, it's definitely the gradient of the whole sequence would be 0. So you will not update the model at all, right? So the norm would be 0. And if you explode, then it's like explode. You having exploding gradients. And if if the value of the gradients would be close to 0, then you have vanishing gradients. But why are such gradients a problem? I mean, so okay, so let's say we get 0 gradients or exploding gradients. Why are they a problem? The point is that in the case of exploding gradients, the learning is very unstable. So you may see that your model jumps, like the loss jumps from low values to the high value. It fluctuates a lot. The other weakness is that the last steps become independent from the early steps. So the main idea behind recurrent neural networks was to capture long distance relations or long dependencies between input tokens. But if the problem, if the exploding or vanishing problems happen, then you lose this dependency. And as the result, you only focus on local context. At each step, you only learn from a few former steps. So the prediction at each step is conditioned only then on a few previous steps, not on really early steps. But it is also important that these problems also happen in multi-layer perceptrons with many hidden layers, where we use the sigmoid activation function, for example. Because if you notice that sigmoid activation function has, usually has a very, very small gradient values. So if you multiply this gradient several times, the value of the gradient gets close to 0. So your model would be independent of the earliest steps or early layers. Okay, but how should you know if your model faces with these problems? There are some symptoms actually that you can recognize that if vanishing or exploding gradients happen, if you have vanishing or exploding gradients. For example, the first sign is that you see a very high loss value on training set or at different iterations. So if you let your model run for several epochs and the loss value on the training set doesn't decrease, the cause of that could be vanishing problem, the vanishing gradients, because the model doesn't learn the relations well, right? Or if you see large changes in the loss on each update due to the model's instability, and it usually happens when you have exploding gradients. As we discussed, loss can become NaN during training. So if you see NaN in the loss value, or you see NaN in the weights values, it's very likely that you you have exploding gradients. Model weights can grow exponentially during training, then you have explosion. So you may not see none, but you still see that, okay, so weights are growing exponentially, like the value of the weights are growing exponentially. So then you should be you should be careful, because the explosion can be the cause of this. You train the model, but the model doesn't learn anything. So that could be because of vanishing. The other symptom is that the training stops at the very early steps of training, of fine-tuning. And further training steps does not decrease the loss. For example, in the first or second epoch, your model gets to the best performance, and then you do not go, you do not learn, afterward. And when I say you do not learn afterward, it means that the value of the loss does not decrease afterward. So in the first and second epoch, the value of the loss decreases, but after the second epoch, the value of the loss doesn't decrease, so it stays fixed. So it's very, one cause could be vanishing, but the point is that if it happens after several epochs, like 5, 10 or something, it could be a sign that your model is overfitting. But just like if it really happens at a very early steps, it could be because the model, it could be because of the vanishing problem. The other symptom is that the weights closer to the last steps would change more than those at earliest steps. Again, it shows that you are independent from the earliest steps, and weights shrink exponentially and become very small, which could be a sign of the vanishing, or the model weights become 0 in the training phase. Let's see how we can solve these problems. For the exploding gradients, the solution is easy. So we can do gradient clipping, which means that just like we check if the gradient of parameters is greater than like certain value, just we replace the gradient with a constant value. So if, for example, we set a threshold for the gradients. So, and if you say that if the gradients is like the value of the gradients for some parameters is greater than like 1, we replace them with 1. So, right. So it's very easy to deal with the exploding gradients. But for the vanishing problems, we need to be more careful. I need also to tell you that the exploding, the gradient clipping is already implemented in any toolkit that you use for training your deep learning model, and you can easily define it as part of your optimization process, and it handles automatically the value of the gradient. So make sure that you always do it to prevent any explosion. Okay. But as I said, for the vanishing gradients, we need to be more careful, because again, the vanishing usually happens because of the initialization of parameter W, and also the activation function that we have for hidden layers. If the activation function, usually, there is a solution that people propose that instead of using sigmoid function, it's better to use a rectified linear unit as activation function. And for initializing the parameter W, it's better to use the identity matrix, which is a diagonal matrix, where all values in the diagonal is set to 1. But maybe another solution for vanishing gradient is to change the structure of the network a bit. The main problem here is happening because we have a deep structure over over a long sequence of inputs, right? So if we can somehow disturb these long relations and we force the model to pick up instead of capturing the relation between all sequences, we let the model to learn which step is more important to be captured for representing the current step, then we can have, or we can deal with this vanishing problem, which defines GRUs and LSTFs. Let's start with GRUs, or gated recurrent units. GRU is, or GRU unit, or like gated recurrent unit, or a GRU, is introduced by Cho et al. And colleagues in 2013. It's only a more advanced method for computing the vector at hidden states for each step. The key idea behind GRUs is to enable hidden states to capture long distance dependencies if that is necessary. So the structure of GRU can look like this. Instead of having a weight like a linear combination of, so let me use my pen. Now here, instead of using a linear combination of the previous hidden state and a linear combination of the input token to compute the value of the hidden state at each step, we assume that hidden state is a GRU unit that takes a linear combination, that takes the input actually vector, the vector representation of the input token and the vector representation of the hidden state in the previous step, and combine them with GRU method. But how? We will see it in the next slides. Okay, GRU works like this. So at the top, we see the current architecture, or we see an illustration of a GRU unit. The input to the GRU, as any other unit that we have in the recurrent neural models, is the vector representation of the input token at time step t, and the value, or the vector of the vector representation of the hidden state at the previous step t minus 1. The main idea behind GRU is that we define a reset gate to say if we should capture the content of, if we should capture or we should retain the content of the memory, or should we reset the values? Okay. So the value of the reset gate here is the sigmoid of the linear representation of the linear transformation of the input sequence or input vector plus the linear transformation of the hidden state. So what is happening here is that the value, so the RT, or like the value of the reset gate, comes from this part, right? So you take the linear combination of the input token and linear combination of the previous hidden state, linear transformation of the previous hidden state, and you combine them. So, and then you give them to a sigmoid function, and sigmoid usually maps the values between or transform the values of the output to values between 0 and 1, right? So that's why it's named a reset gate. So based on the the value of the hidden state in the previous step, and the value of the input token. Reset gate learns if we should keep or if we should remove the value, the content of the memory. As I said, in any neural layer or any neural component, the best way usually to combine is that you multiply the input by some matrix, and then you sum them up. So that's why the gate is defined like this, right? So you multiply each input like xt and xt minus 1 by some matrix, and then you sum them up. So this is the way that you do in neural model always. So you shouldn't, I mean, although like simpler approaches, you can just sum them up. You can just avoid using any weights or this. But if you do any of these ideas, you are involving your heuristic and your thoughts in the model design, which is not that much interesting. It's more interesting that you involve your thoughts in the way that model learns the knowledge automatically itself. Okay. By the way, so we calculate the reset gate as we discussed. And based on the value of the reset gate, we can calculate what could be the output of the hidden state, right? So new memory content could be, so let me use another color. Okay, new memory content could be represented by HT. I mean, like tilde HT, or let's call it tilde H, which is the tangent hyperbolic of linear transformation of X and linear transformation of the hidden state in the previous step times by the reset gate. This sign here this sign here is point-wise multiplication. So if you have a matrix, here as the output, you multiply that by you multiply any element in this matrix by the value of the reset gate. So you are saying that, okay, so how much value or how much content should you memorize from the previous step, and how much content should be forgotten, right? And or should be reset. But the point is that the value of the current input has a complete impact on the memory content. Okay, so if you look at HT, like the value of HT, we see that HT is the tangent hyperbolic of XT, which completely transformed by matrix U and moved to the tangent hyperbolic function. And the other input comes from this way, right? Which is HT minus 1 times matrix W, and also point-wise or element-wise multiplication by the reset gate. So you say that if we reset this value, then if we reset this value and combine some part of the memory with the current input token, what would be the output, right? What would be the content of the memory? So this is HT. Let's change the color to something else. Now let's clean it. We also define another gate for update gate. So we say, okay, if we do not reset, but instead we update. So if we decide to completely update the gradient, so if we want to completely update the memory, so we say the update, we define some update gate like ZT, which is the input of, which is a linear transformation of the input token plus the linear transformation of the hidden state by a sigmoid function. So if you look at ZT, ZT is the sigmoid of XT, or maybe green is not a nice word, nice color here. So let's change it to something else. Yeah. So if you look at ZT, ZT is a linear transformation of XT. The other input comes from here, which is the linear transformation of HT minus 1. So we say that this is the update gate. But why is it called the update gate? Because the final memory encodes a combination of the current content and its content in the previous time step. So because the final memory value is our HT is the update gate based on partial based on the new memory content and the previous content. So when we have a completely keep the previous content, right? So if we look at the update gate, it's like the formula that we use to compute the final memory content. It's like we, based on the ZT, based on the value of Z, we decide how much, we decide if we should update the memory or just we should rely on what we have learned from the previous steps. In terms of the language, let's say if you are processing a sequence and you see some articles like the, a, or something like this, that usually happen a lot in a sequence, like in a sentence or in a text. Maybe for these, we do not need to update the content of the memory, right? Because, I mean, we don't want to define it extremely, but just like, I'm gonna give you some idea why we need to decide if we should update the memory or just we don't update it and we leave the memory or like the value of the hidden state in the previous step directly, right? So for many articles or many determinants, maybe we don't need to update the parameters because they are not content words. Many of words in the language could be a stop word. So they do not carry any meaning. So just like they do not have many impact on many NLP tasks. But I mean, for several, they have high impact, but for many, they do not. The point is that what we want is that we want the model learns this property automatically. So the model should learn for which step it should update the memory, and for each step it shouldn't update the memory. So let's say if in here we define a combination like how much we should learn, or if we should learn anything from the memory, or if we shouldn't learn anything from if we should completely use the previous step, or we shouldn't use any, or we should update the memory based on the current input, right? And if you want to update the memory based on the current input, then the current input is the partial value of the previous hidden state. So you will not use the whole content of the memory, but you let the model to use only part of that to update the value of the hidden state. Okay. To have a better understanding, let's say we play with some extreme cases of these reset gate and update gates. What are the extreme cases for the reset gate and update case. There are, we know that these values or changes between 0 and 1 because they are the output of the sigmoid function. But the extreme case is for the extreme values for these variables or for these gates are 0 and 1. And let's start with the update gate. If the update gate equals to 0 and we equals to 0 here, oops, here, we notice that this part becomes 0, so and this part becomes 1, so we only have ht equals to ht minus 1, which means that you say the current input token or the input token at the current step doesn't have any impact on the content of the memory. So what we know or what we have in the memory at this step is what we knew in the previous step. So nothing has been changed. All right. Okay, but why does it help to solve the vanishing problem? Because when you say there is nothing has been changed, it means the value of the gradient for parameter W just to move to transform the knowledge from the previous state to from the hidden state and of the previous step to the hidden state of this step or current step is 0, right? So when the value of the gradient is 0, then you do not update anything. So no vanishing also happens, right? So there is no vanishing gradient here. Okay. But what happens if the value of the update gate is 1? Then it means that this part is 0 and this part equals to ht, which means ht equals to the new content of the memory. Which means, okay, in other words, you want to update the content of the memory based on or conditioned on the input token. The only point or the only difference with the standard RNN is that you do not update the whole memory completely. So you let the model to decide how much the content should be reset. If you remember, we defined a tilde h or the new content, the new memory content, as the tangent hyperbolic of linear transformation of the input token and linear transformation of the previous step times a reset gate. So we do not use the value or the content of the hidden state of the previous step completely, but we let the model to decide how much of this content should be used for the memory at the current step. If the reset gate is 0, it means we do not use any information from the previous step, right? So the value of the memory at this step, it mainly relies on the content, right? So we reset the memory completely, right? So meaning that we forget the past. So we forget the past. So it's like we break the rule, we break the network, we break the RNN structure, recurrent steps, and we make it 2 parts because the gradient will not go back from this step, right? So we forget the past completely. And if RT equals to 1, then we have a standard RNN gate. We have a standard RNN gate. So we can compute the vanishing gradient. The beauty of this model is that you do not push the model. You do not use any heuristic to train the model, or where you should stop training, or where you should stop training, where you should update the parameter. So it's like when you use GRUs, the model learns automatically which step is important to be used for computing the memories, and which steps is important to be used for, can be ignored actually for to avoid vanishing and exploding gradient issues. Okay. The other solution was proposed by Hochreiter and Schmidt-Huber. Its name is long short-term memory cells, or LSTMs. These LSTMs are like GRUs. They are some computation units for calculating the memory, for computing the memory vectors. And they usually, I mean, these units, LSTM units, have more parameters than what GRUs units have. Here is the architecture of an LSTM unit. The LSTM unit contains of 3 gates: input gate, forget gate, and output gate. For the input gate, the value of the the value of the gate is as we discussed, a linear combination of the input token and the hidden state. So you want to condition based on the input token and the hidden state. So you say you multiply each input by a matrix and you sum them up, and you obtain a gate value. You give it to the sigmoid function to get it like a right gate, right? So xt is the input and ht minus 1 is the input to the I gate. So here is the I gate. So just you check how much you should be able to write here. The other gate is forget gate, which is again a linear combination of input tokens given to the sigmoid. So the given sigmoid, so this is the forget gate. So ht xt, you give it to the forget gate. So it captures how much you should forget from the memory. The other one is the output gate, like the linear combination of the input and previous on the hidden state of the previous step, to know how much you should move to, for how much you should move for to the second step, to the next step. Something that I want to mention here is that the concept of the gate is very useful in neural networks, so try to learn it in general. It helps you, or it helps a neural model to automatically learn, control the behavior of the connections or the behavior of the contents. It's important that the output, the activation function of a gate should be, or is always sigmoid function, because you want the values between 0 and 1, and you want the model to filter the values automatically. So whenever you want to filter some connections in your neural model, you usually shouldn't do that manually. It's better to use for example, a sigmoid function, and then the sigmoid function can learn which value of the input should be filtered out. Okay, so just I wanted to mention this. Now we can go to the output part. As the output of the LSTM, we get HT, which is like the hidden state representation at this time step. HT is the output. Is the multiplication, is the point-wise or element-wise multiplication of the output gate times tangent hyperbolic of CT. What is CT? CT is the value or the final memory cell and it's obtained from here. So it's the difference between LSTM and GRU is that we carry to between different time steps, we transfer two vectors. One vector is ht minus 1, and the other vector is the context, or ct minus 1. So from each step, or for computing the value of each step, we rely on three inputs: ct minus 1, ht minus 1, and xt, or like the value of the input token, xt, the value of the hidden state in the previous step, ht minus 1, and the value of the context in the previous step, which is ct minus 1. But what is this ct minus 1, and how is it calculated, computed? Ct is, look at this, ct is coming from ct minus 1. So it's more or less the context that we have from the previous step. But some part of that, it needs to be forgotten, right? So we need to forget some part of this context. And then we combine that with the current information that we get from the input token, and we use it as the context for the next step, right? So we say that the final hidden state, or HT, is the forget gate, the output gate, I'm sorry, the output gate, I'm sorry, let me clean this part. So HT comes from here, right? HT is the output gate times the output gates times tangent hyperbolic of the context CT, and then you give it to the HT. So actually, you are saying that the whole memory could be not useful for representing the current hidden state. More or less, for having HT at this time step, we may not need the whole content of the memory. That's why we define some output gate. So the output gate just determines how much the content of the memory, or to what extent the content of the memory should be used for representing the current hidden state. In GRU, we always assume that HT, whatever that we have as the output, or whatever that we have as the representation of the memory, is useful for the current hidden state. In LSTM, we say no. We let the model learn how much of the content of the memory should be used for representing the current hidden state. So if we say that CT or context, or just like a memory, the content of the memory at time step t could be sufficient or could not be sufficient for the final hidden state, right? Representation. Okay. Final memory cell, or CT, is okay, but how should we calculate the memory cell? So it's like the forget gate, as we discussed, times by CT minus 1. So we say that, okay, from the content of the memory in the previous state, we may decide to forget some part of it. And we also have some input parts. So just like we calculate the new content of the memory based on the current input. So we have XT. So that's why we use CT by the combination of or tilde CT by the combination, by linear combination of the current input token and the value of the hidden state in the previous step. And then you get CT bar, or it's tilde CT. And so you say, okay, how much of this content should be used as the input to the memory? Should be, or how much content of the previous memory should be forgotten? And then you can combine these two together as the new content of the memory. What I would like you to do is to sit down and go for the extreme cases. Check what happens if each of these gates would be 0 or 1, and then try to understand how LSTM helps you to avoid vanishing issues, vanishing gradients in RNNs. Okay. No matter what unit you use, a standard RNN or basic RNN, GRUs or LSTMs, there are different extensions to recurrent neural networks. Maybe the first extension is bidirectional RNNs. So by RNNs, if you use LSTMs, it's still named by LSTMs. If you use GRUs, it's named by GRUs. The main idea is that we use two RNNs with two different sets of parameters. One RNN for processing input symbols from left to right, and the other RNN for processing input symbols from right to left. So it's mainly useful for having good context representation. So why should we only have the left context? Why not using the right context? But is it really important to use the right context? Yes. For many languages, for example, adjectives can come or can appear after the noun, so not before the noun. So adjective can be on the right side of the noun. So it's helpful to have the bidirectional inputs or bidirectional context. In this sense, the final representation of each step is the connection of the outputs of these RNNs, like HT is the concatenation. Like the hidden state at each time step is the concatenation of the forward pass and backward pass, or is the left to right pass and the right to left pass. So technically, it's very easy to implement it, right? The only thing that we need to do is that we change the order of the input. So instead of processing inputs from X1 to Xn, the only thing that we need to do is to reverse the list, and we process that from Xn to X1, right? And we give it to the second RNN. But current neural models already have these bidirectional settings. So just there is a flag in the input. So just you set it if you want to have bidirectional or not, which is always suggested to use bidirectional if you can. Why shouldn't you be able to use bidirectional? For some tasks, you may not have you may not have the right context. For example, for language modeling, you generate a language from left to right, right? At least in generative language modeling, you try to predict the next word from left to right. So you do not have access to the right side or the right context of the language, of the sentence. The other extension is a deep by RNN. So you can have different layers of RNN. So instead of having one layer in RNN, you can have different layers. The main idea is that you combine these hidden representations. Over each other, so it gets very complicated. But like the computation of the gradient will be done by current deep learning frameworks. frameworks, but there is a risk of vanishing gradient, vanishing and exploding gradients. So this one, I mean, for implementing the deep bidirectional, deep bi-RNNs, you can easily define the number of layers that you want for your RNN when you are constructing a model. The point is that so far the connection between steps are defined based on the connections over hidden states. But what happens in the language is that the output that we predict at each time step affects the output that the output of the current or the next time steps as well. So the idea is that the output tokens can be connected to each other. So based on the value that you predict at each step, you can give it to an embedding function and then inject it as the input to the second or to the next output layer. So there are different approaches here. So since the task is sequence prediction, you can also use CRF method. You can use the CRF method to connect the output layers. For PyTorch, there is like a package for CRF RNN so that you can easily define CRF on top of this. Okay, in this slide, I would like to talk about some applications of RNNs in natural language processing. As we discussed, RNN is very, very helpful when you have a sequence prediction or when you want to process a sequence of inputs. Probably when we talk about the sequence prediction task in NLP, everybody thinks about part of speech tagging. The input is a sequence of words and the output is a sequence of POS tags like noun, verb, determiner, and so on. And for each word, you want to assign a POS tag to that word, right? So in this task in part of a speech tagging task, you want to assign a POS tag to each word in the sentence. The second task is named entity recognition. The input is a sequence of words and the output is a sequence of name entity recognition tags. For example, we usually use BIO labels. B shows the beginning of a named entity, and I shows that this token is inside of a named entity, like an O is outside of any named entity. So it's the word that is assigned to tag O doesn't belong to any named entity. So, and the idea is to say which words in a sentence represent the person name, which words in a sentence represent a location and the organization, and which words represent the time, represents some time. And so the idea is like this. So you have a sequence of words and you want to assign each word token like BPR, like the beginning of the person name, or like, and the second word is like the inside of that, or so on. So since you have a sequence as the input and you want to do the sequence prediction, you can use RNN. Next task is language modeling, or LM. The input to the language modeling task is a sequence of words that we have as a context, and the output is the word that you want to predict as the next word, right? Or it's still a sequence of words. So like a sequence of the following words. At each time step, you want to predict the next word. So at time step 1, you want to predict the second word. At time step 2, you want to predict the third word. The point is that the word that you predict at each time step can be used as the input or to the second, to the next time step, but since this word can be wrongly predicted, you can use the true word that you have as the input from the input sequence to feed to the next step. The other task is sentence classification. The main idea is that for sentence classification, we do not have a sequence prediction task. Instead, we have only one, or we have sequence classification. So we have a sequence of tokens, and we want to assign a label to this sequence of tokens, right? We have a sequence of words as input, and we want to process them. And we know that these words in the sequence are related to each other. But the output is one label for the whole sequence. The only trick is that you use the hidden state of the last step to represent the whole sentence. The main idea is that if the hidden state represents the whole context, or all words that are in the sentence, then the last hidden state represents the value of the last hidden state, represents the content of the whole sentence. So it can be directly used or it can be directly taken as the representation of the whole sentence. The other point that we should notice is that maybe the other trick that is shown to be useful for obtaining a sentence representation from RNNs is to take the average of all hidden states. Because when you use the last hidden states, the gradient needs to backpropagate through the all tokens or all steps that we have. But when you use the average, you use some skip connections. You use some skip connections to distribute the gradients over different time steps equally. We will go back. We will actually come back to this topic again in the next lecture, and we discuss of what is the best way to combine these hidden representations to obtain a sequence representation for solving a sequence classification task, or even a sequence generation. Like machine translation can be take a sequence of words in a language and generate a sequence of words in another language. Just to wrap it up, in this lecture we discussed about RNNs. We have seen that they are mostly useful for sequence prediction, although they can be also used for sequence classification tasks. The main motivation behind RNN is to process a sequence of inputs where elements of the sequence depend on each other. And when you want to have the output representation of at each time steps, where the output is conditioned on the current input and previous tokens or previous steps, we usually use RNNs. RNNs faced with vanishing and exploding gradient issues, like multi-layer perceptrons, when we have a very, very deep layers, or when we have very, very deep architecture. And the solution for the exploding gradient was gradient clipping. That just, if the gradient goes beyond a certain threshold, we replace the gradient with that threshold. But for the vanishing, we discussed two approaches, like LSTMs and GRU units. And the main idea behind GRU is to let the model learn which hidden states, which content should be used in the memory, or by giving different importance to different steps. So the model should be able, in GRUs, the model should be able to learn which time step should be considered to define the content of the memory, and which time step can be skipped, and in this way, the gradient can be easily transformed to the long distance or like to the early steps of the RNN. We discussed about LSTMs, and LSTMs define the LSTM takes two inputs. One input is the memory cell, which captures the content of the memory through the whole architecture, and the other input is similar to the standard RNNs, which are HT, the value of the hidden state at the previous step, and the value of the input token at the current step. And the main idea behind LSTM is that you have these this memory cell over different time steps, and at each time step, the hidden state is an adaptation of this memory cell. And then we discussed several applications of RNNs, like for sequence prediction, like when for each items in the sequence you want to predict the tag. And they also talked about like sentence classification, that you can use the last hidden state, or like the hidden state of the last token, for representing the whole sequence. Or you can use the average over all words or all hidden states in the sequence to represent the whole sequence. That's it. Yeah, thanks for participating in this lecture. Please ask your questions and put your comments either in our GitHub or in the Moodle. We would be happy to address them. So see you in the next lecture.